Hello guys. So in this video I want to discuss an interesting question that whether is space-time as we know it, is space-time emergent from some deeper structure? Because a lot of physicists and scientists and even ordinary people recently there is this is a very hot topic for debate, and a lot of people are discussing if space-time is emergent. Now, what do we mean by if space-time being emergent from something deeper, and if and what is this something deeper, and why this idea all of a sudden that space-time needs to be emergent, space-time might be emergent? So I have discussed emergence in a lot of my previous videos and my writings, but let me be clear. Let me clarify that that was a different kind of emergence, because I discussed emergence in context of complex systems like consciousness. So to explain complex systems, the complex phenomena or behavior of complex systems, then that is in that case, in that emergence, the question which we're trying to address is that how this complex behavior, this complex phenomena emerges from the underlying simple parts. What is it that is in the parts or their arrangement or their interaction that gives rise to the emergence? But here we're talking about the emergence of space-time. What is space-time in general? Space-time is the backdrop of the universe. It's everything, all of our theories in physics, everything which we're describing, we're doing it in space-time. Everything is happening in space-time, at some point in space and at some point in time. That is the most basic assumption in all our theories of physics, right? Now, when we're talking about the emergence of space-time, we must first of all we must ensure that whatever space-time is emergent from, that does not contain this inherent concept of space and time within itself. Like suppose you are trying to explain the emergence of consciousness from the neurons in the brain, suppose, and you are assuming that the neurons themselves are conscious in the same way that we are conscious. I'm not saying any lower level of consciousness. Then where does the neurons consciousness emerge from? Then that means you're not really explaining the emergence of consciousness, right? You are kind of moving in circles. So similarly, if you're trying to explain the emergence of space and time, we must make sure that whatever the underlying, the deeper theory or deeper framework from which space-time is emergent, that does not contain any notion or any concept or any idea of space and time in it. We need to explain how this idea of space and time emerges from them, from that level. But at that level there should be no space-time, right? Otherwise, if space-time is present in that level also, then what is the point in saying space-time is emergent from that level? Then consciousness is emergent from the parts of the brain. That means the parts of the brain are individually not conscious. They individually do not exhibit this property of consciousness. Consciousness is emergent from them as a whole. Same thing here. Now the point is that, but it's very difficult, because when we say that in terms of consciousness and that kind of emergence, we say that the arrangement between the parts and the interaction between the parts, these things play a role. But whenever we're saying arrangement between the parts, like that could be neurons in our brain or whatever, it could be any complex system, not necessarily the human brain only. And it could be any complex phenomena, not just consciousness. But when we're saying arrangement between the parts, that means there is a concept of space there. We need to, we are taking into account, we are taking into consideration like how they're arranged in space and interaction. That means there's a concept of time there, because interaction means suppose two parts are interacting or more than two parts, whatever. But if some parts are interacting, that means it is giving rise to some changes. Otherwise, there is no point in saying that the parts are interacting. If nothing changes at all, like it need not be like the particles are colliding, not that, but yes, some kind of change must be going on, whatever. Otherwise, the interaction means some change is going on, and to be able to register that as a change, we need a concept of time. So in this kind of emergence, there is a inbuilt notion of space and time. But when we're saying space-time is itself emergent, that is an entirely different kind of emergence, and here we need to make sure that you know what I'm talking about, like space and the deeper theory or the deeper level of understanding, that does not have any notion of space-time from which space-time is emergent, which I'm telling you time and again. But it's very difficult to do, because our usual ideas, space-time is a very fundamental instinct, fundamental concept which is built in human beings. From time immemorial, we have this concept of space and time, like inherent concept. Yeah, maybe our ancestors long back, maybe they did not know about the equations of space-time, they did not know about four-dimensional space-time and everything, but we have this notion. Everything we say, everything we do, we inherently assume that space and time, this concept. So it's very difficult to completely get rid of space-time and yet build a theory that makes sense. Because that is a limitation of us humans, of our understanding. That's not necessarily a mathematical limitation, maybe. But yeah, now let me discuss like why suddenly all of a sudden this idea that space-time needs to be emergent. What's the problem? Yeah, back in Newton's time, we thought that yeah, there was this space in which things are happening, and there was this time, which was like this universal clock, which is constantly ticking at a constant rate, which is kind and which we can use as a reference to measure the time interval between two events. Then comes Einstein with his revolutionary theory of relativity, and he says that no, space and time are should be kept in the same footing. He kind of unified space and time, the three space dimensions, and he treated time as the fourth dimension, and then he kind of knitted them together into this beautiful fabric called space time. And in Einstein's theory, space-time is no longer a constant background. It's interacting, and it's changing constantly in response to whatever is happening. I mean, it takes part in the theory. That's what technically we mean that it's background independent. I mean, it's no longer like in Newton's time, like there is some universal time or everything. Time dilation, space length contraction, every space-time perceptions and space-time vary between observers. And all these things, right? It's no longer constant. It takes part in the theory. That was Einstein's view. Then yeah, then this quantum mechanics and everything. But recently we are maybe some physicists are claiming, and I will tell you why, that maybe even this view is not complete, because Einstein's fundamental theory of gravity, which we call general relativity, it contains the seeds of its own demise, kind of. Because see, in general relativity, although it's a very successful theory of gravity and it has been verified experimentally as well, but general theory of relativity is kind of, it does not work at very small scales, or when at very high energy levels, or at very small distances. It does not work, because the equations of general relativity itself predict the existence of black holes, which are kind of as we all know, they're very dense regions of space time. And once if something falls inside a black hole, we cannot, I mean, it's kind of completely lost forever, just very roughly speaking, right? And right, even light cannot escape black hole. I mean, all those qualitative ideas we all have, right? I assume you also have. But yeah, what do we mean by black hole is that it's a region in space time inside which our equations simply do not work. We do not know what happens inside a black hole. We have a lot of new insights like ADS-CFT correspondence or the holographic principle, and we have a lot of calculations about the entropy of a black hole, Wittgenstein, and all these things. The surface area of a black hole, but still we do not have a complete understanding. Like Einstein's equation can give you a very good prediction about ordinary matter, like which has not yet collapsed into black hole. Any ordinary matter in ordinary body in any region of space time. But inside this black hole, inside this singularity, and where the density is very high, I mean, at very small length scales and very high energy, the equations simply do not work. And that means then this is why we think, physicists think, that maybe we this points at that this indicates that there is some deeper theory, deeper understanding. Because if space-time is fundamental, if space-time is at the root of everything, if all of our theories can be, I mean, if space-time is absolutely fundamental, then there should not be any region of space-time which our theories cannot predict, we cannot cannot understand, or which kind of just doesn't make any sense. That means because if we stick to our classical, which our conventional notion of space-time, then we cannot really understand what happens inside a black hole, what happened at the very beginning of the Big Bang, singularity, and all this things we cannot know. So then, to understand all these things, maybe we need a deeper theory which maybe does not have any in itself does not have any idea of space-time. But yeah, when we understand this, when we study the theory, we can probably understand, that is the idea anyway, that is the hope anyway, that space-time emerges from this from that theory. And yeah, since general relativity breaks down at the extremely small scales, because that is why we this idea, that is the origin of this idea that space-time might be emergent. But see, in science, like any theory is not and it cannot be assumed to be, cannot be given the status of an established scientific theory until and unless it is, I mean, it has at least some amount of strong empirical support, experimental evidence, experimental support. But I mean, all the experiments we do, I mean, whatever, even if it's a class, high school experiment, you're just measuring, you're just verifying Ohm's law, or if it's an undergraduate level experiment, maybe you are measuring Planck constant by doing some photoelectric effect experiment, or you're doing some electronic experiment, or if it's an extremely advanced experiment, like you're colliding particles at the Large Hadron Collider in Switzerland, and you are trying to understand, maybe trying to study new particles of the Standard Model, whatever it is, I don't care. But all experiments, they have some, I mean, you must I mean, they have elements of space and time in them. Like for instance, you're doing an experiment, yeah, you need to measure that constant, or whatever you're trying to do to estimate that, to estimate this, in all experiments you have some concept of time, like okay, so this is the time taken for this change to happen, so that means this. Or you have some concept of space, like from this point to that point. I mean, whatever, if you completely do away with the notion of space and time, then you cannot then I mean you cannot do any experiment at all. There is no experiment possible which to make sense of which, yeah, maybe you can do the experiment, but to make sense of your results you need some concept of space and time. Then how to verify a theory which has no concept of space and time in it? The thing is that we need to make sure, we need to first of all understand and very, very precisely understand at that how exactly space-time emerges, the notion, or should I say the illusion of space-time emerges from this deeper theory. First of all, we need, once we find this theory, if we do suppose, then we need to first of all we need to jot down, and we need to very precisely understand how our notion of space-time, the space, this concept, this space-time as we understand it, how this emerges from the first principles of this theory. Because once we complete doing this, then we can, maybe it's possible, I mean it's at least possible that then we can devise some experiments. By studying the results of these experiments, maybe we can say that whether they follow this rule, that how the space-time is emergent, and then we can get some indirect verification of the fundamental theory. That is possible, but yeah, we need to keep this in mind, because this theory is different from any theory we have dealt with so far in physics, because it has no notion of space and time in it. It's more abstract than anything we have dealt with so far. That is, it's kind of, that is what we need to keep in mind at all times. Okay, so now, and one more thing is that uh, some people, like there is some an alternative concept, like there is this idea that space time might be emergent, because see, there are some I was recently reading a quantum magazine article. Just in fact I will drop the link in the description for you guys, the quantum magazine, I actually follow their articles and they're very good, for the general audience. They explain a lot of important and recent developments in fundamental science in very simple words. So recently they did a series kind of about this topic, and I mean that's where I got the idea of this video, in fact, that the emergence of space-time. So yeah, and the thing is that so yeah, like I said, the basic idea. So the article which I was reading was that there are three thought experiments which kind of show why our current understanding of space-time is not complete. Now, whether this means that there is a deeper understanding of space-time, a deeper level of understanding from which space-time is emergent, or whether this means that our understanding is incomplete and we can modify our present understanding without having to do away with the notion of space-time altogether, that remains to be seen. I mean, there are two schools of thought. Like, one is that yeah, space-time, I mean, we need not completely forget space-time, completely do away with the notions of space-time, but we need to modify our understanding, modestly modify our current understanding of space-time to take into account of, I mean, to account for all these things. And the second school of thought says that no, space-time is not fundamental; it's emergent. We need an entirely different level of understanding. We need a radical shift in our worldview. So yeah, it remains to be seen. I mean, both of these schools of thought, they have some. I mean, both of them have some strong logic, and yeah, we'll discuss that slightly. But first, let's discuss these three thought experiments. I mean, they're kind of related to one another, But in that quantum magazine article, I'll drop all the links in the description. If you're interested, please check them out. But they described it like this, So I've just I'll just discuss it here. I've just made the 3 points, and I'll just elaborate in not very briefly, not very long. Okay. So basically, so yeah, the space-time fabric of Einstein. I mean, in Einstein's general relativity, we have this space-time kind of fabric, which I already told you. It's not fundamental because, as I told you, when we try to apply the rules of quantum mechanics to Einstein's theory, see, quantum theory it's a successful theory for explaining a certain level of reality and the three forces other than gravity. And general relativity is a successful theory which explains gravity see, general relativity is an experimentally verified, established, successful theory which explains a particular level, which explains the universe at a particular scale, and at a different scale quantum theory works. So we cannot say that this is right and that is wrong. Both of them are right, but it doesn't seem likely that there are two different theories at different levels, because we have been trying to find out similarities between this theory, and most extreme hope of physicists is to unify these two theories into a single theory. But whenever we try to reconcile these two theories, like then I mean, we are met with nonsensical results and things that simply don't make sense, which is surprising and which is kind of disappointing, because we don't expect the universe to be described to, I mean, it's unlikely that the universe is described by two fundamentally incompatible theories at different levels. I mean, it's okay if the theories were different, but at least they were compatible. But they as of our present understanding, they are kind of incompatible. There are of course many proposals of unifying them, like string theory and everything, anything, but and stuff like that, loop quantum gravity. But we have yet not been able to completely and satisfactorily answer all the questions regarding this, right? So that is why that is the basic motivation. Like there are two theories which do not agree with each other, and they are successful in their own at their own level. So that means this must mean that there is some deeper theory which we do not yet understand, from which these two theories are kind of emergent at different level. For instance, many years back, we thought that ice and water vapor, they are something entirely different. Ice is a cold, solid, like kind of stuff, and water vapor is kind of gas, right? So, what is the similarity between? I mean, yeah, in those days, people maybe thought that ice and water vapor, they are entirely different kind of things. But some people probably thought that maybe they are emergent from something, some a deeper level of understanding, and then came our understanding of water molecules. That means we are going one level down, that we are going at the level of molecules, at the molecular level. That no, at the molecular level, ice, water and water vapor, they are all made up of the same molecules, the H2 of the water molecule, right? Two hydrogen atoms and one oxygen atom. So at that level they are the same thing, unified kind of. But from that molecular level, under different conditions, like if the temperature is high, then we get water vapor, and if the temperature is sufficiently low, we get ice, and all these things. Like under different conditions, from that level of understanding, this ice, water and water vapor, they're emergent kind of. And apparently at our macroscopic level, it seems like ice, water and water vapor are incompatible, but they're not. Just a rough analogy, right? So similarly, maybe with our limited understanding at this level, it appears that Einstein's theory is not compatible with quantum theory. But maybe there is a deeper understanding, deeper level of understanding, which we are trying to find out, from which both of these theories are emergent, right? That is our goal. Okay. So you see, if I try to apply the rules of quantum theory to Einstein's theory, then we cannot, at like I said, at very short distances, we get nonsensical results, which means Einstein's theory is not complete. I mean, simply breaks down at such short distances. So that means it's not a complete theory. That is what we can say from this, right? Like see, in Hawking radiation and everything, the black hole you don't even need to go to the black hole information paradox. Just simple idea of Hawking radiation. Black holes, the conventional idea of black hole, it came from Einstein's field equations and different solutions, right? But then in quantum theory, there is this concept of antimatter, and then these vacuum fluctuations. Constantly, these particles and antiparticles are kind of popping up and annihilating each other and everything. Now, if I try to apply this rules of quantum theory to Einstein's theory, like if I say that what if this such a particle-antiparticle pair pops up at the event horizon, or roughly speaking at the boundary of a black hole, then what? Then before they get the chance to annihilate each other, one particle is pulled in by the black hole, and it's completely, and the other particle is that particle which is pulled in by the black hole, that it cannot annihilate the other particle, so the other particle kind of survives. But what accounts for the energy of the other particle? Because initially it was vacuum, right? Particle antiparticle pairs can pop up because it's allowed under the Heisenberg's uncertainty principle, that for a brief period of time you can borrow energy from vacuum. I'm not going into the mathematics, but you can roughly speaking, you can borrow energy, kind of materialize, and then you can annihilate each other and just release the energy. So it's not really a violation of the conservation of energy, but it can happen, and it has been observed also. Like Casimir effect and all. It's not just a theory; it has been experimentally observed. But if this happens in the event at the event horizon of a black hole, then we run into some problems, right? So this is just an example why problems arise when we try to apply the rules of quantum theory to general relativity. But some people say that maybe we don't know the right rules to apply, and maybe modest mathematical modifications on our present understanding can save space-time. These people believe that there is no requirement for a radical understanding, or there is no need to completely forget the concepts of space-time. Maybe some modest mathematical manipulations can do the trick, can do away with all these problems. But space-time will still survive. Because I was reading this another article in Quantum magazine also. This guy called I forgot his name actually. Just a second. Latham Boyle. He's kind of a theoretical physicist. So he believes that using appropriate symmetries. You see, he basically studies the standard model of particle physics, and I myself worked in quantum field theory and standard model also. And in standard model, there are a lot of symmetries. SU symmetry groups, you need to have a good understanding of that. SU2 symmetry, SU3 symmetry, and even some people are trying to apply more exotic kind of symmetries. I mean, non-conventional symmetries to the standard model to solve certain problems, because the standard model is a lot of problems. It's not a mathematically elegant theory and everything. See, in the standard model of particle physics, it's a good theory. It's successful theory. It has made a lot of good correct predictions, and it's a very successful theory because it describes all the three forces except gravity. But the problem with standard model is that there are a lot of arbitrary parameters which can be tweaked to get the desired result. It's not a rigid and unique theory yet. And to kind of constrain or limit these parameters, we use these symmetries. Like recently there are these symmetries called non-invertible symmetries. Then I did some work in modular symmetry also. I as part of a research fellowship which I was awarded recently by the Indian Academy of Sciences. I dropped a video also about modular symmetry. It's mostly the mathematics part, but anyway. I mean, I'm still working on it. The research is still ongoing, so it's not. But anyway, this guy Latham Boyle, he believes that maybe using appropriate symmetries, maybe we can kind of find an equivalent description of the singularities or these regions of space-time where Einstein's equations don't work, and maybe we can deal with without needing to completely do away with the notion of space and time. I mean, without the need of a radical change in the space-time concept in our current understanding. See, I'm quoting Latham Boyle himself. Fermions, or the particles which make up the matter, there are basically two kinds of particles, fermions and bosons. So fermions are spin half particles. That means the spin is an intrinsic property. It's not like it's spinning like this. It has no classical analogy, but it's kind of, and this concept of spin, it's not just a theoretical concept. It has been verified, Stern-Gerlach experiment and everything, Stern-Gerlach experiment. And it was actually predicted theoretically, then from Dirac's theory and many other things. So spin half means, roughly speaking, this particle, if we assume that spin has some classical analogy, that is spinning like this, that means it needs to spin 2 times to come back to where it started from. That is what we mean by spin half. And fermions are spin half particles, but bosons have integral spin. But fermions have half integer spins. So yeah, fermions, as Latham Boyle is saying, that fermions interact with space-time in a funny way. If you spin them around once, they actually don't come back to their initial state. Instead, you have to turn them around 2 times. That is what I told you, right? Now, in this and other respects, it's as if space-time has a two-fold structure that only fermions can see. Because if I'm a spin one particle, then I cannot see this hidden kind of two-fold structure. So Latham Boyle says that since fermions are this kind of two-fold, the spin half particles, so it's almost as if like space-time has a two-fold structure which only fermions can see. And using mathematical techniques and symmetries, maybe we can, have an equivalent description of ordinary space-time. Maybe we can, it's a different description. Latham Boyle is not saying that the current understanding of space-time is correct or complete. No. But he's saying that instead of assuming that space-time is emergent from something deeper, some entirely radically new different level of understanding in which there is no notion of space-time, he's saying that maybe we can find an equivalent mathematical description of space-time where there is the notion of space-time even in this new description, but it's equivalent to the ordinary space-time. And if we use this equivalent description, then these problems will not arise, the singularities and everything. See, this is a kind of extremely mathematical, and it's still a work in progress. Such a description has been proposed by a lot of physicists, including Roger Penrose himself. But yeah, it's not. It's still in work. It's still in progress, right? I mean, we're just kind of finding a mathematically equivalent description means it will look very different, but it's equivalent, and it can explain all the phenomena that our present theories can explain, plus it can take care of singularities, while still not completely doing away with this concept of space-time, the notion of space and time. But yeah, now finally, before I end this video, let's discuss these 3 thought experiments which I have been talking about, which show why our present understanding of space-time is incomplete. I mean, this we can definitely say that the present understanding of space-time is incomplete. Now, whether we need whether these problems can be solved by a modest mathematical modifications to our present understanding, or whether space-time is emergent from an entirely different level of understanding, that remains to be seen. But definitely our present understanding of space-time is incomplete. We can say that for sure. And why? Here are 3 illustrations. For instance, how small, see, at our level, everyday life, say meters, then millimeters if we go smaller, then picometers, femtometers. The nuclear dimension is femtometers, which is 10 to the minus 15 meters. So, if I ask you to probe smaller and smaller distances, I mean, how small can we get? Can we go? Can we probe? So, how do we probe smaller and smaller distances? We do that by colliding fundamental particles, subatomic particles. That is what particle accelerators or particle colliders do. Because if we collide particles, then we a lot of maybe a lot of new particles will be generated and everything, and the machine will detect that, and we can get some, some on the computer we can get some data, and from there we can generate graphs and stuff, and from there we can say a lot. We can even predict the existence of new particle, of what will be their mass, energy, and a lot of things can do. But anyway, the idea is that to probe smaller and smaller distances, we need to collide particles. And yeah, I'm talking about particles, subatomic particles, electrons, or even smaller particles. So that means, see, to collide these particles, I mean, it's not like just a soft collision. You have to accelerate the particle to very high velocities, and then at near light velocities, in fact, and then collide them. Only then we can get an idea about the internal structure. If two cars collide at a very high speeds, only then they kind of break down, and they kind of kind of, you know what I'm talking about, right? They kind of break down, and maybe the internal structure gets revealed, kind of. I mean, but if the cars kind of bump into each other softly, then the internal structure will not get revealed. The cars will not even get deformed. I mean, right? So with that, and that is a good thing in case of cars. But in this case, we want to accelerate particles and collide them at very high velocities. That is why these particle accelerators, they have a huge radius and all these magnetic fields and stuff. They have to accelerate the particle, charge particles, and a lot of other stuff is there to very high velocities, and then to collide them. But that means the particles are we are talking about very high energy particles. A particle with high velocity definitely has a lot of energy, and the wave associated with the particle then must have a very small wavelength, because small wavelength, high energy means small wavelength. They are inversely proportional, right? H over P equals lambda, de Broglie relation. You can understand it whatever way you like, because even in uncertainty principle, I mean, anyway, energy and wavelength, they are inversely related. This is a very basic concept. Like red light has the longest wavelength, and is the lowest energy, because wavelength, long wavelength means kind of the wave is more spread out, the frequency is less, right? Frequency and wavelength, they're inversely related, because the speed of light is frequency times wavelength, and energy is proportional to frequency. That is for the very starting point of quantum theory. So energy is proportional to frequency, that means energy is inversely proportional to wavelength. But see, high energy small wavelength, that means if we try to probe, suppose at very high energy particles, we can probe very small distances. But we try to, but there is like, we think that there should be no limit. Like we can probe 10 to the power minus 15 meters. Why not 10 to the power minus 15 billion meters? Why not 10 to the power minus 15 quintillion meters? Whatever. I mean, there is no limit. Numbers don't end. But but since we are talking about physical particles, the constraint is that as we are going to, just the hypothetical scenario, if we are considering, like we are going on increasing the energy of the particles, but at some point the energy will be so high, or the wavelength will be so small, because high energy means small wavelength, right? And longer wavelength means low energy. I think I told the opposite just a few seconds back. I'm sorry. High energy means small wavelength, because energy and wavelength are inversely related. But yeah, so the high energy means if you want to probe a small distance, the wavelength should be small. Otherwise, if the wavelength is large, then that particle, I mean, wavelength of what? Of the wave associated with the particle. Because in quantum theory, we know that with every particle we can associate a wave particle duality. But if the particle has a low energy and if a long wavelength, that means since the wavelength is long, it cannot enter that distance. It cannot probe small distance. To probe very small distances, we need high energy or low wavelength, I mean small wavelength particles. But but after a certain point, we cannot just go on increasing the energy of the particle. If the particle reaches very high energy, that means it will collapse into a black hole, right? Because energy and mass, they are kind of the same thing according to relativity, and high energy means high mass means very high density, and it will collapse into a black hole. But once it collapses into a black hole, that means that particle will never reach our detector. That means we cannot measure that distance. I mean, we are measuring the distance, we are probing the distance. That means we need to detect the particle, right? But if the particle collapses into a black hole after a certain extent, after a certain threshold, our detector, it will never reach the detector, and we will not be able to measure that distance. That means after a certain point, that we technically call the Planck length. I mean, Planck length is the smallest length which we can physically measure. I mean, even we have not reached there yet, but yeah, theoretically we can measure up to Planck length. But after that, it's not possible to make any measurements of length. It's the kind of shortest possible length that can be measured, Planck length. Then there is this Planck units, Planck time, Planck energy. Planck energy is kind of the highest possible energy, and a lot of things are there. And I mean, the expressions for Planck units can be derived easily from the standard equations. But yeah, now the point is that if we cannot make any measurements beyond Planck length, I mean for lengths which are smaller than the dimension of the Planck length, that means maybe space-time as we understand it does not exist there. Because if space-time existed at that level, if space-time works, that means we should be able to make measurements, but we can't. So this is the first thought experiment and the first idea, first indication that yes, maybe space-time, our current understanding of space-time is not complete. At some levels, this understanding of space-time simply breaks down. So maybe we need a deeper theory or an entirely different kind of understanding, kind of level of understanding to describe, to completely get a grasp of what is happening at that level. Second thought experiment is that in quantum mechanics there is some uncertainty inbuilt in the theory, and if you are measuring the position of a single electron, then it's uncertain. I mean, position and momentum, according to Heisenberg's uncertainty principle, they are canonically conjugate variables. So if you try to measure the position very accurately, then you are kind of compromising on the accuracy of your momentum measurement, and vice versa. So, but anyway, even I mean, you cannot measure the position and momentum of a particle simultaneously with 100% accuracy. I mean, you cannot. But yeah, so there is always an uncertainty. I'm just not going into the mathematics, just giving a rough description. But that is for a single particle. Now, if but that means suppose we have a say a ball, a cricket ball, or a football, or I mean a soccer ball, whatever, or maybe a car, a bus, an airplane. So we more or less we know the position, we can pinpoint the position as well as momentum of this particle, of these bodies. But they are also made up of the quantum particles, atoms, electrons, quarks, whatever. So how is this? Because thing is that when we're adding more and more particles for a many particle system, for a single particle system, yeah, this uncertainty is not negligible. But for a system which is made up of many such particles, many such fundamental particles, small particles, this kind of the uncertainty reduces drastically, and we can make see when we do experiments in our lab, basic classical physics experiments, then there is no uncertainty, right? Yeah, there is an error, measurement error, like this is the zero error, or I mean not zero error, there is this least count of the instruments. We cannot measure a distance which is smaller than the least count using that instrument, and all these things are there. Then if you're doing some experiment where you're using a stopwatch or something, then the least count of the divisions of that watch, then that corresponds to time measurements, whatever. But that is due to your instrumental, your apparatus, that is due to your instrumental limitation, apparatus limitation. It's possible to build better higher resolution measurement devices also. But uncertainty principle, this quantum uncertainty, that is not due to any our limitation or our experimental limitation, apparatus limitation. That is a fundamental feature of the universe. I mean, it's theoretically not possible no matter how advanced devices we build, right? So don't confuse those two, right? Uncertainty principle is not due to any our experimental error. It's a fundamental feature of the universe according to quantum theory, right? Quantum mechanics. And another question is then so suppose we are so quantum uncertainty then decreases if we increase the number of particles in the measuring device. Suppose we want to measure anything of a particle, say it could be velocity, momentum, position, whatever, and we want to measure this as accurately as possible. So to make a measurement of a particle, the particle must interact with the measuring device. Otherwise, how will you make a measurement? Suppose you're measuring the position, that means you have to shine light on it. If you're using a photon detector, light detector, you have to shine light on that region in space so that you can say that okay, the particle is at that position. You can make a measurement. But yeah, again, light is a form of energy, so that will again affect its momentum. And I mean, anyway, but without in any way interacting with the particle, you cannot make any measurements. But still, since we need to make an accurate measurement, we want to disturb the particle as little as possible. We want to reduce the uncertainty as much as possible. So we are kind of adding more and more particles to our detector, to the measuring device, because like I said, for a big system with a lot of particles, the uncertainty is less pronounced. The uncertainty reduces drastically. So, but to measure accurately whatever we are measuring, then we are going on adding more and more particles to our measuring device. But after a certain level, if we go on increasing the number of particles indefinitely, after a certain level, the density will increase so much that our measuring device will collapse into a black hole. Okay. And once that happens, we cannot measure anything using that measuring device. It will stop functioning as a measuring device because it has collapsed into a black hole. We cannot do anything with it, right? So we cannot measure the desired property with the device after a certain limit, right? So that means since it's impossible to exactly define physical properties of an object in space-time, to exactly define, right? Yeah, at our level we can more or less make very precise measurements, but yeah, since it's not possible to exactly fundamentally define, then maybe we need some new framework, and this is the second thought experiment. Yeah, this is a thought experiment because theoretically, yeah, we cannot make a 100% accurate measurement. For practical purposes we can, but yeah, this is the thought experiment. And since we're talking about fundamental physics, theoretical physics, we need to take into account. It's not like it's okay. I can measure the velocity of my car with almost 100% accuracy, and my so why even bother about that? Yeah, in that case, why even watch this video? Why even bother about theoretical physics? But we guys, we need to bother about this. Those of us who are interested in theoretical physics. The last thought experiment which I want to discuss finally before I end this video is that suppose we're trying to store more and more information within a fixed volume of space-time. Suppose first of all so that means see hard disk drives and whatever yeah, I'm sorry about that. So we're trying to store more and more information. So if we use that means we need to use more high density material, and that means we're kind of increasing the density of that fixed volume to store more and more information within the fixed volume, because storing information means you need some density, you need some matter that will store the information, that will represent the information, that pattern or whatever information you're storing. That is how computer disks and everything works, right? But if it go on indefinitely increasing the density of a fixed volume of space-time, again it collapses into a black hole. But here, this last in regards to this, I want to discuss something interesting. See, amount of information that can be stored inside a black hole, according to calculations, it does not depend on the volume of the black hole, on the volume of the space-time region, which is the black hole, but it only and it entirely fully depends on the surface area of the black hole. It has been shown by calculations. I'm not going into the details. I even myself don't know the details of this particular calculation, but yeah, this is the idea, and this is a very very well established idea in physics currently. That means, so from here the idea arises that probably any event happening inside a black hole is recorded on its surface, and just by studying the surface, I mean, kind of all the information is etched on the surface of the black hole. So the inside of the black hole is the volume. That means it's a three-dimensional region of space-time, but the surface area, or just the surface, it's just a two-dimensional structure, right? The surface. So that means if everything that's happening in a three-dimensional region of space-time has an equivalent representation, has a correspondence with a two-dimensional structure, it's just like a hologram. You see those hologram stickers on books and on stuff, they appear 3D if you look at it, those stickers, but they're actually just a sticker on a surface. They're actually two-dimensional, but they kind of contain all the information of a 3D object. And yeah, even more advanced holograms are present. From here, in fundamental physics, we have something called the holographic principle, and this is from where the idea is coming from. It's more technical. It's called the holographic duality, or ADS CFT duality or correspondence. ADS is anti-de Sitter space, and CFT is conformal field theory. I mean, both of this, one is the two-dimensional structure and the other is the 3D space. Kind of it's a duality, means it's a kind of correspondence between two-dimensional theories and three-dimensional theories, because if we can kind of find an complete equivalent mathematical representation of mathematical two-dimensional representation of our three-dimensional theories, yeah, just a second. So yeah, if we can do that, then we can kind of see if we can kind of find a complete mathematically complete two-dimensional description of our three-dimensional theories, then we can kind of deal with all of these problems, singularities, in a much better way. And this is why basically the duality concept is used in a lot of areas in physics, in modern theoretical physics, because the idea is simple. Kind of you have a problem which you cannot solve, which you don't know how to solve, the mathematics is unsolvable. Maybe you don't know how to solve it, or maybe it's fundamentally unsolvable, whatever. Then what do you do? Okay, I cannot approach in this path. So maybe I can find a different but equivalent mathematical description which I know how to work with. If I can show that this is equivalent to that, and if I can solve this, then I have technically solved this as well, although I have not directly solved this. Even not just modern holographic duality, we have been using this technique long back, even in Fourier transforms, or in general integral transforms. What we do, suppose if it's very difficult to solve some particular integration or differential equation, or I mean any complex, what we do, we kind of transform it to a different space, right? In signal processing, time space to frequency space. Why we do this transformation? No, because it's easier to solve the problem in that space than in this space. In this space, it's almost impossible or very difficult to solve the problem. So let's just transform this problem using some integral transform to the different space, solve the problem there where it's a lot easier, and then once we get the solution in this space, we can simply apply the inverse transform to get the desired solution in this space. Kind of an indirect way, but it works. It's easier because direct way doesn't work. Same thing here, almost, I mean, the same approach, same idea here. Of course, it's much more difficult and not exactly the same thing fundamentally, but yeah, you get the idea. So, but yeah, so coming back to the third experiment. So yeah, maybe since black holes and in extension all of space-time, so then maybe all of these are kind of holograms, holograms which are living in some 2D surface. They are of some unknown nature, and this unknown nature, this is what we're trying to find out. Maybe our 3D space-time is emergent from this deeper structure, because a complete two-dimensional description is possible. That's what I'm trying to say. And these thought experiments kind of suggest that space-time fabric that seems to form the universe we inhabit. This fabric breaks down at extreme circumstances. I mean, very small distances or very high energies, whatever. Our mathematics, our theories simply don't work at that level. So, and since this space-time seems to break down at that level, then we may need a deeper description of reality that doesn't fall apart, comprised of more fundamental. We need a deeper description of reality which is comprised of more fundamental building blocks. And we also need to show how our present understanding of space-time is emergent from this deeper level to be able to make sure that our new theory is experimentally verifiable. And according to some people, maybe we do not need any radically new theory. Maybe like I already discussed, that is also one thing to keep in mind. And yeah, I think you have heard about John Wheeler. He's a very interesting character and really like that guy. He recently died. I mean, not recently, maybe 10-15 years has passed by. So he was a physicist who seemed to think, he worried a lot about these questions, and he was a very, maybe he's not as famous as Einstein and all, but he's a very, he has made many significant contributions to the field of physics, and he's kind of unconventional type of physicist, and I really admire that person, John Wheeler. So John Wheeler he gave this theory which I'm sure you might have heard of it. It's called it from bit. So he thought that maybe space time and everything is emergent from information. He told that information is at the fundamental. I mean, information is the most fundamental thing, and he gave a proposal, a kind of theory, whatever you say, that we are living in a participatory universe where kind of our questions create the world, because in quantum mechanics, in quantum erasure thought experiment, and some experiments and some thought experiments are there which seem to suggest that the future can affect the past, which kind of doesn't make sense, I know, when you think about it using your common sense notion of reality, but yeah, these things are there, plus a lot of other things. So according to Wheeler, very like roughly speaking, what he assumed, or what he believed, is that space-time is indeed not the most fundamental level of description of the universe, but it's information. Like even in context of black hole information paradox, where in all of this you need this concept also. This holographic duality also plays an important role here. But yeah, that is what Wheeler said. Wheeler believed that information is at the root of everything, and by information, it's not like. There is what do we mean by information? Then all these things, there are a lot of definitions, many definitions of information, Shannon information, there is an entropic interpretation of information, a lot of things. Then more modern approaches also to information. Information theory is very important theory, actually. Very, especially modern, in modern times, there's a lot of kind of applications in information science. But Wheeler believes that let me kind of give you a simple example what he mean by this participatory universe. He gave a thought experiment which is called the negative 20 questions, because he told that we are kind of creating the universe, he was himself not sure what he was speaking about, because in his old age he was kind of very confused, and not just for his old age, it's really actually confusing. Wheeler was attempting to answer the ultimate question, so obviously it's not an answer that you can look up in Google or in ChatGPT, right? But just an illustration, it's not strictly relevant to emergent spacetime maybe, but let me just discuss this anyway, and then I'll end the video. I mean, if you have watched till this far, and if you're only here for the emergent spacetime, then you can just stop watching at this point. But yeah, the it from bit thought experiment, or the negative 20 questions, just an illustration, a thought experiment of how our questions can create something which did not exist. Like for instance, I play a game with you. Very simple thought experiment. But I'm just give a simple illustration. The negative. Why is it called negative 20 question? Suppose the conditions of the game is that I tell you that you think of something, anything. It could be whatever, a house, uh, a bacteria, a human, an airplane, a tree, a volcano, maybe a comet, a planet, whatever, anything. So I ask that you think of something. Don't tell me what you have thought of. Just think of it, and I will ask you binary questions. What do you mean by binary questions? That questions whose answer can be either yes or no. These kind of questions. Like I cannot ask you what is your name. What is your name is not a binary question, because the answer to what is your name cannot be yes. What is your name? Yes. What is your name? No. That's not possible, right? So it's not a binary question. But if I ask you, does your name start with A? The answer could be yes or no. The answer could be either yes or no. There is no other possibility. So it's a binary question. Is the third letter of your surname Y? The answer could be yes or no. So these kind of questions, what I mean by binary question. So, and this is how, information is defined. Like how many binary questions, this is one way to define information, to be more precise. How many binary questions I need to ask to be able to successfully guess at the information, at what you have thought. Suppose you have thought of something, I don't know what. That is the condition of the game. And I'm asking you binary questions. So how many questions I need to ask? Maybe after a million questions, I can narrow down the possibility. And I said that based on your responses to my million questions, yes, no, 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 yes, whatever pattern, maybe then I can kind of make an educated guess that yeah, you thought of an airplane based on your responses. I think this is the idea of the game. But now here's the interesting part. Suppose I told you that you think of something, you told yeah, I've thought of something. Now you start asking your binary questions, but in reality you have not thought of anything. Suppose you have not thought of anything, but then you say that I'll be asking questions. How will you answer if you have not? Suppose I ask that is the thing small or big? Then what if you have not even thought about anything? What will you answer? So is the thing small? What will you answer? Yes or no? So maybe you follow a pattern. Like maybe I'll follow the pattern. Yes, no, no, yes, yes, no, no, yes, yes, no, no, yes, yes, no, no, yes. Suppose you follow this pattern. You have not thought of anything in your brain, but you just follow this pattern. You're not even registering the questions, the binary questions which I'm asking. You're just kind of I'm asking questions. And you're just yes, no, no, yes, yes, no, no, yes, and so on. Or maybe you are following some more complicated pattern. Yes, no. I mean whatever. But you're following a pattern, or maybe or even you're just randomly answering yes or no. That's possible. You have not actually thought of anything. But if this continues for maybe say 100 questions, 1,000 questions, then even if you initially did not think of any particular object, any particular thing, after a sufficiently large number of questions and after your responses, we will narrow down. We will get. We will narrow down on a particular object. We are kind of narrowing down means we are removing the other possibilities and we are kind of getting fixed. And after a sufficiently large number of questions, we can I can kind of say that okay, based on your responses, I'm sure that you thought of this. And suppose I say based on your responses, I'm sure that you thought of a rabbit. And maybe it's true. It's logically true based on responses. But the thing is that initially you did not think of any animal. You did not think of a rabbit initially. So that means my questions, kind of created this rabbit. Kind of that is the thought experiment idea, right? And the important part is that the way you decide to answer is plays a crucial part. Suppose if you follow the pattern yes no, or if you follow the pattern no yes, it's different, because suppose you have not thought of anything. The first question I ask you is that whatever you think of, is it big or small? And you say yes. Then I ask you, is it so? Okay, so I ask you, is it small? You say yes. The next question is it alive? Is it a living thing or a non-living thing? You say, the question is it a living thing? You say yes. So suppose you're following the pattern yes, or maybe let me just complicate things further. Maybe you're following the pattern yes no, and the first question I ask you is that whatever you have thought of, is it small in size? You say yes. The next question is it non-living? You say no. Right. Now I ask the same question, but you instead of yes no, you change the pattern to no yes. So the first question is it small in size? You say no. Is it non-living? You say yes. Right. I have asked the same question in the same order. You have just changed your pattern of answering yes no. The answer can either be yes or no, right? So in the first case, you say that yes, it is small in size, and in the second question, you say that no, it is not non-living. That means it is living and it's small in size. So the answer could be a bacteria, an insect, an ant, a small living thing, right? But in the second case, although I ask the same question in the same order, you say that first you say no. That means you say that no, it is not small in size. That means it is big in size. Next question asks that is it non-living? You say yes. So it's a non-living object which is big in size. So it could be a planet, it could be this Earth, it could be a star, it could be a galaxy. I mean, yeah. So I'm not going into discussions on whether any spiritual discussion that a planet is conscious, this Earth has some kind of consciousness. But yeah, I mean, it could be an airplane, for instance. An airplane, you will not claim that an airplane is conscious. It could be an Airbus A380. It's a huge non-living object. So that is this. I think I was successfully able to illustrate like how this can happen. Your order of answering matters. That is the only thing that matters. Even if you have not initially formed a picture of something in your mind, just by playing this game, we can create something. And Wheeler said that at a fundamental level, though it might not be clear to you exactly how at this point, but he said that maybe this is how we are creating reality. I mean, not by asking questions, obviously, but we play a participatory role in the creation of the universe, and all of this, links to information theory. It from bit. Why did Wheeler call his idea "it from bit"? It means it, some object, something, the matter we see around us. That is what Wheeler refers to as it. But it is coming from bit, it from bit, and by bit we mean those binary, these bits, qubits, those information term. I mean, that is just a notation, but yeah. So it's kind of an information theoretic description or information theoretic view of the world. That is what I was trying to say. But yeah, the information theory is very interesting topic also. But that is for, let's keep it for another day. The main point of this video was to give you an idea or why space-time, whether space-time is emergent. I mean, of course, nobody knows the answer, of course, but I just gave you a brief overview about where we currently stand in terms of understanding space-time, and where we and what are the future directions that research in this area might take. And I'll also drop some interesting links about the same in the description. Please check them out. And thank you guys for watching this video. Thank you very much.